In today's video, we're going to be looking at another tool we have to take derivatives of more complicated functions. Kind of like product rule, chain rule, quotient rule, those are all tools we had to break down more complicated functions into simpler parts that I knew how to take the derivatives of. Well, same kind of thing in today's video. Here's an example. Y squared minus y equals 3x squared minus 2x plus 10. Why is this function more complicated? Well, normally, we're used to seeing functions in this form, right? Y equals some function of x, right? You've got your output variable all by itself on one side of the equal sign, and then the other side of the equal sign is your function, right? What's going on? What's your rule? And that's completely in terms of x. And so then if I wanted to take the derivative of it, I could just focus solely on just whatever that function of x is, because it's completely in terms of x, and I can take the derivative in terms of x. But if I look at this equation's special because if I tried to solve for y, I can't do it. It's impossible to solve for y, to get y by itself. This is still a function because it relates how x and y are related, but it's impossible to get y by itself. It's impossible to isolate y. So does that mean I can't take the derivative of this? Well, it turns out I still can. I can still take the derivative of this in terms of x. Recall that's one of my notations for taking the derivative. I can still take the derivative in terms of x. The short answer to this, to oversimplify it, to take the derivative of this, take the derivative of everything. I'm going to take the derivative of everything, both the left side and the right side. I'm going to take the derivative of everything I see. Okay. So if I just focus on the right side, if I just focus on this right side of the equal sign, well, that's what we're used to, right? My derivative of 3x squared minus 2x plus 10, well, that's just 6x minus 2 plus 0, which I don't have to write the plus 0. So the right side's simple enough because it's completely in terms of x. And notice I'm taking the derivative in terms of x. But what do I do with the left side? Well, this is where this process of implicit differentiation comes in. This is what implicit differentiation is all about. And if it turns out that implicit differentiation really is just the chain rule in a different form. Okay? If I want to take the derivative of this, but it's all in terms of y, well, I can just do some quick little manipulation to change this around. Notice that I can rewrite d over dx, right? This represents take the derivative in terms of x. Well, with just a simple manipulation, I can turn this into dy over dx times d over dy. Right? Do we see how those are equal? I have a dy in the numerator and a dy on the denominator that if I cancel those out, I'm just left with d over dx. So, by just multiplying, doesn't that look familiar? We've seen something like this with chain rule, right? So, by multiplying by dy over dx, I can now take the derivative in terms of y. So, if I look at this, if I look at just this left side of the equal sign, well, I can, by multiplying by dy over dx, I can now just take the derivative of this in terms of y. So I can just treat the y's as x's, take the derivative like normal. I get 2y minus 1. But remember, in order for me to do that, I need to multiply by dy over dx. So interesting. What do I have here? Well, what was our goal in the first place? To take the derivative of this function. And if I look closely, that's exactly what this represents. Dy over dx, that's just y prime. Right? That's my derivative. That's my derivative of my y function. It's the derivative of y in terms of x. So by just doing some simple division to finish this off, I get y prime, or dy over dx, is equal to 6x minus 2 divided by 2y minus 1. So even if I don't have, so what did we just talk about? Even if I don't have my function in my normal form that I'm used to seeing, I can still find a derivative by using this process right here, this process of implicit differentiation. Okay, let's try this with a different example. Okay, let's try this with an implied example. Okay, let's look at another example of implicit differentiation. So here we have a ladder leaning up against a house. Okay, we're going to call this ladder 15 feet. So we have a 15-foot ladder leaning up to the wall. Okay, and I'm going to label some distances here for us. So I'm going to call this distance right here y, from the top of the ladder straight down to the ground along the side of the house. And then this distance along the grass, I'm going to call x. Okay, the distance from the base of the ladder to the house. Well, the problem with this ladder is that it's sliding down. Okay, so my ladder is sliding down this way, and this distance is sliding down that way. Okay, so what we're going to try and figure out is what is dy over dt. Okay. What do I mean by this? What does dy over dt even mean? Well, if I use that notation, I'm talking about a derivative. What's the derivative of y in terms of t? What's t in this case? Time. Okay. So, and here I'm going to go and we're talking about seconds here. So t in this case is the seconds. And we already labeled what y is. Y is this distance along the side of the house. So what we're going to look at, what we're going to try and calculate is, how is this distance over here changing? How is that distance from the top of the ladder to the bottom, to the ground, how is that distance changing over time? Okay. Now, if the ladder were stationary, this would be 0, right? If that ladder wasn't moving, that would be 0 because that distance isn't changing. But because the ladder's slipping down, this value should be non-zero. In fact, is it going to be positive or negative? Okay. Theoretically, this should be negative. It should be less than 0 because that distance is going to be getting smaller. My ladder is getting closer to the ground. Okay. So let's see if we can figure this out. This is an interesting question, though, because, well, if I'm taking derivative, I need an equation to take a derivative of, right? I don't really have an equation. The closest thing I have to an equation is, what type of triangle am I working with here? This is a right triangle. So I could use Pythagorean's theorem to write this equation. Well, that's a start. But I'm taking the derivative in terms of what variable? I'm taking the derivative in terms of t. Well, since the equation that I wrote doesn't involve t at all, this turns into implicit differentiation. This is where I actually need implicit differentiation to help me. Okay? So, let's do this. Let's see if we can do this here. So, when I take derivatives, remember, if I'm separated by addition, I can just take the derivatives of these separately. So I'm separated by addition, so let's just focus on what is d over dt of x squared. Well, that's not the right variable. So I need to use implicit differentiation. And what that boils down to, like before, is I can go ahead and write this out if you want. This boils down to dx over dt times d over dx. That allows me to take the derivative of x squared in terms of x, and I get dx over dt times 2x. So that's what I get for my first term. Well, what about my second term? What happens when I try and take the derivative of y squared? I have to do the same thing, but instead of switching it to d over dx, I need to switch it to d over dy. So I'm left with dy over dt times 2y. And then what happens to the right side of the equation? Since 225 doesn't depend on time at all, it's constant, it's not changing, the derivative is 0. Okay, so now I have an equation that actually deals with dy over t. So we see that, that's what I'm looking for, dy over dt. Well, it turns out in order to fully solve this problem is, sure, I could go ahead and solve for dy over dt. And what does that leave me with? That leaves me with dy over dt equals negative dx over dt times 2x all over 2y. So you'll notice that dy over dt, it depends on three different things. It depends on what x value you're at, it depends on what y value you're at, and it depends on how fast this distance is changing. Right? How is your x value changing as over time? So let's say I gave you these values. Let's say we're paying attention to when x is 9 feet. So when the ladder is 9 feet away from the house, 15 feet up in the air, not 15 feet, sorry, 12 feet. Oh my goodness. And when the base is moving 2 feet per second away from the house. If I gave you all three of those values, then it's fairly straightforward to just plug those in. Dx over dt is 2, x is 9, and y is 12. Put that all together, and you get, negative 36 over 24, which is just negative 3/2. Which, once again, what is this dy over dt? It's how that distance is changing. So this is negative 1.5 feet per second. Okay, so let's see if I can generalize implicit differentiation. Let's break it down to kind of in its simplest form here. So let's say you have some function of a variable y, but you want to take the derivative in terms of x, right? In terms of a different variable. So anytime you're taking the derivative of a function that's in one variable in terms of a different variable, well, you can use that little trick. I can manipulate that by just doing dy over dx times d over dy. So by multiplying by the derivative of y in terms of x, I can now take the derivative of this in terms of y. Okay, so what does that give me? That simply just gives me dy over dx times f prime of y. In other words, if you're ever in this situation where you're taking the derivative of a function that's in terms of y, but you need to do it in terms of x, you just take the derivative of that y function like normal, as if you were taking the derivative in terms of y, but when you're done, multiply it all by dy over dx. And that really is implicit differentiation in a nutshell. Okay, let's look at a quick example. Let's look at another quick example. What if you have something like this? And I wanted to take the derivative of this, right? I wanted to find dy over dx. Well, the first part's simple enough, right? The first part, that's what we just barely covered. So I have a function of y, but I want to take it in terms of x, right? Because I'm looking for what is dy over dx. I want the derivative of this in terms of x. Well, like we said before, right, all I'm going to do is I'm going to take the derivative like normal, like it was in terms of y. I get 6y. But then when I'm done, I multiply it all by dy over dx. What about this piece? How do I take the derivative of this? Because this term is in terms of both x and y. It has both of those variables in this term. Well, the key here is recognizing that the way I deal with this is recognize that I'm multiplying these two variables, x times y. With that in mind, what I can do is I can use product rule. In fact, that's how I have to do it. I have to tackle this using product rule. I do that by just saying, okay, my first function is x, my second function is y. When I take the derivative of each of these, f prime, once again, remember, I'm taking the derivative in terms of x, so the derivative of x is just 1. G prime, the derivative of y is just 1, but because I'm taking this in terms of x, I then have to multiply that by dy over dx. Right? I have to use implicit differentiation on this one. Okay. And so then using product rule, I put that together, right? F times g prime, so I get x times dy over dx plus f prime times y, 1 times y. And then, of course, the other side just goes to 0. So if you ever see this situation, we're not going to finish this one, but because this is really what I wanted to highlight. If you ever see this situation, you have to tackle it using product rule. You have to treat it as two different functions being multiplied together and use product rule to actually evaluate. Okay, last thing I wanted to cover is what if we're going back to this equation that we started with. Because I know that in order to find the first derivative, right, dy over dx, I need to use implicit differentiation, mostly because of that left side. But what if instead I wanted to find the second derivative? How would I go about doing that? Well, the key to understanding how to get the second derivative is just recognizing that the second derivative, right, if I want to find y prime or y double prime, the second derivative is just taking the first derivative and taking the derivative of the first derivative, okay? So with that in mind, what I can do is I can go back, revisit what we already did and say, okay, well, I already got the first derivative. So break that down to where I end up with, yada, 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 do all that same work again, including, you'll notice my last few steps were getting dy over dx on its own side, right? Solving for dy over dx, solving for y prime. So this is what I ended up with. Okay, so the key to finding the second derivative is getting to this point and then taking the derivative again. Okay, so when I take the derivative again, right, since this already is isolated to where it's just y prime, that left side is just going to become y double prime. And I can just focus on this right side. How am I going to take the derivative of this right side? Well, that requires quotient rule. Okay, so I'll use quotient rule to tackle this derivative. I get 2y minus 1 times right bottom times the derivative of the top. The top is all in terms of x, so my derivative here is just 6. Minus the top times the derivative of the bottom. Well, the bottom's in terms of y, which means I need to use implicit differentiation. I'm going to take the derivative like normal as if it were x, but then I'm going to multiply it by dy over dx. All over my bottom squared. Okay. So there's my second derivative. Now the problem with the second derivative is it's in terms of 3 different things. Okay, it's in terms of x, y, and it's in terms of dy over dx. Now I can handle it being in terms of x and y, right? That's how I had my first derivative. My first derivative was in terms of y and x. The reason why I'm okay with that is because it's impossible for me to solve for y. So I have to just keep it in terms of x and y. But three different things is a little overkill. Can I get dy over dx in terms of x and y? Well, of course I can. Because what's dy over dx? That's the same thing as y prime. Right? dy over dx just represents the derivative of y in terms of x, y prime. Do I know what y prime is equal to? Absolutely. Right? That's what we started by doing, is we found what y prime was equal to. So that means I can rewrite this as 2y minus 1 times 6. You'll notice I'm not simplifying, and that's on purpose. Okay. 6x minus 2 times 2 times 6x minus 2 over 2y minus 1. All over 2y minus 1 squared. Now it's completely in terms of x and y. Okay. Now the reason why I'm not simplifying is to highlight the fact that I think a lot of these problems, especially the ones where you're finding the second derivative on your homework, it won't tell you that you need to simplify. So once I substitute my y prime function in so that everything's in terms of x and y, that's enough. I can stop there. You can go and submit your answer like that. Okay. Perfect. So that's implicit differentiation. Please let me know if you have any questions as you're working through your assignment, and I'd be happy to help you out with them. Okay. Have a great day, guys.